Hello everyone, thank you so much for joining us today. I hope everyone's doing well and staying safe. My name is Victoria and I'm a Senior Business Development Coordinator at 2H Offshore. With many industry events and conferences cancelled due to COVID-19, we've put together this series of live webinars to keep our valued clients and colleagues up to date on the latest happenings in the world of riser and conductor engineering. I want to welcome you all to our webinar today entitled An Enhanced Analysis Approach for Complex Wells. Before we get started, I'd like to cover a few important housekeeping items. Firstly, this webinar is being recorded and will be made available to you soon, so please look out for a link to that in your email. Secondly, if you have technical or content-related questions today, please feel free to ask them at any time. You can use the Q&A box that is located on the right-hand side of your screen. At the end of the presentation, we'll go through as many questions as we can, but if you have further questions, please feel free to contact our speaker directly. And with that, I'm very happy to introduce our speaker today, Dave Roberts. Dave has 24 years of engineering and fieldwork experience in well design and construction. His first decade in the oil industry was spent in field roles running wireline and downhole tools in numerous onshore and offshore basins worldwide. Subsequently, Dave has specialized in the mechanical analysis of casings and completions, both in operator and service company positions, and has amassed experience in complex well types. Dave is currently 2H's technical manager for well engineering based in Aberdeen, a position he's held for 4 years. Dave holds a bachelor's degree in mechanical engineering from Liverpool John Moores University. So with that, I'll pass things over to Dave to get us started.
Thank you, Victoria, for the warm introduction. Hello, everyone. I'm excited to be here today speaking on this topic, and I hope you will find all the information useful. An overview. When faced with a complex well situation, you basically need to be making the right decisions, and quite often that decision relies on using the best data. Getting that data isn't always easy. The analysis can be tough, and the reason for that basically is the world is a complex place, and it's quite hard to replicate from an analytical point of view. So for an outline for this webinar, I'm going to talk about what makes the scenarios difficult to model. Is there a theme? There's usually a theme to the reason that these situations are challenging. I'm going to talk about the software tools that are available and the ones that we commonly use, their limitations, their pros and cons. And then I'm going to talk about the analysis approach that we've used to address these complex situations. It's a combined simulation solution. So it's not a piece of software or anything. It's a methodology. It's like a workflow. We term this approach CSIM because the oil industry loves a good acronym. So that's the acronym we use for this. So CSIM. I'm going to there's going to be a summary at the end and a number of case studies, which is probably the most interesting bit of the webinar. So what makes the scenarios challenging to analyze? One of the most common reasons for the situation being difficult to replicate from an analytical point of view is because something is non-standard or maybe unusual. These can be broadly classified into 3 kind of areas. They're often related to components of the well, so maybe tools or accessories, for example. They could be unusual loading conditions. From a well's perspective, normally when we look at a load case, it's normally based on a change in temperature or pressure. That would be a typical well engineering load case. But it could be more complex than that and more involved. So that could be a reason that these are difficult to analyze. And then lastly, it's probably because a mechanical well failure or degradation of the well or deterioration. Something has failed or it's seen some material loss. My office is based in Aberdeen in Scotland, so we deal with a lot of wells in the North Sea. The North Sea is quite a mature basin, and a lot of the wells and well stock in the North Sea is a significant age. So the well failure and deterioration is a big factor in some of the complex situations that we look at. And regardless of how simple the well is, when deterioration occurs, it can add substantial complexity to the analysis. So firstly, we'll go over those three areas. Well components. That diagram on the right is a schematic of a DST string, so it's a drill stem test string. And you can see it has multiple ODs, IDs, there's quite a large selection of tools in there. And we're expected to verify that as a primary barrier in a well test, which is, it's an exploration kind of phase of the well. There's a certain number of unknowns which are going on. So it's a, relatively high risk stage of a well's life. Now we're expected to verify that as a primary barrier. And what we see is when we do the analysis, we put it in our tubular design package and we get the schematic on the right. And quite often we see it as just a section of tubing with a packer on the end. And the question is that sufficient? Is it accurate enough? Some of the complexities are involved in the tools themselves, like complex geometries. So we've got multiple outer diameters. We've got multiple inner diameters. Some of the tools are dual wall. It's quite common for these tools to have atmospheric chambers in them or cylindrical pistons. Quite often, sometimes the tools are even not pipe form, so that can be complex. When we look at the data for these tools, the data might not be in the right format. It's quite common to get things like maximum annular pressure or maximum tubing pressure ratings. And what we're really looking at from a tubular design package point of view is a differential pressure. There can be missing data. It's quite common to not see compression values. Normally we like to put in compressive values, not just you will get tensile values for the tools, but it's quite often you won't get the compression value for the body of the tool. And then there's even the tool function itself. Some tools have a preload that are exerted on them. Liner top packers, for example, they have a hold down force that's applied to them for the hold down slips. There can be movement of the tools themselves. So there's a number of packers which show mandrel movement upon packer setting, and that causes a preload in the completion. And the question is, are we capturing all of that detail in our analysis? Are we capturing it with our models? Next one could be loading conditions. We've got there's three sort of schematics of wells there on the right. We've got two subsea wells, one in kind of drilling mode with a riser and BOP attached. Then on the right we would have a sort of example of a platform type well. You can see the loading conditions they're not just as simple as just a well load. We've got environmental conditions. So those blue arrows, we've got loading from wind, waves, and the current is acting on some of those strings in the water leg. The vessel and rig itself, there's a riser load that's applied to the well. Even a platform and a jack-up, a floating rig, they all have riser sections. There's always a stack up on top of the well in certain phases. The well might be supported by tensioners. There's direct loading on the top from surface equipment. And then we've got the operations that are ongoing in the well itself. So we've got temperature and pressure conditions. Temperature is a huge force generator in these wells. So depending on what you're doing, so production is obviously a hot condition, injection would be a cold condition, stimulation probably cold and high pressure, so you've got pressure and temperature acting there. So the fact is, looking at these individually in isolation is not sufficient. The real world uses a combination of these factors to load tubulars and well structures, and we should really be, in our analysis, we should really be capturing all of those loading mechanisms and modeling the full combination simultaneously. And the third area was the mechanical well failure and deterioration. So corrosion, obviously, as wells age, they corrode. You're going to be losing material either through sloughing or, which is a typical aerobic corrosion material loss. Pitting, which is more associated with CO2, sweet corrosion maybe. It can be internal or external. So modeling the material loss, it's different if it's from the inside of the pipe or the outside of the pipe, so that can be challenging to model. Drill through wear, that's that bottom right picture there. You can see that drill through wear, that wear groove is actually cut right through into the thread form there. So we should be modeling pipes with the correct wall loss assumption, because they're only as good as their worn condition. You can't assume that the pipes are new. That can either be measured or it can be simulated or even just assumed is quite a common method of accounting for drill through wear. Lastly, axial movement. Axial or lateral movement, particularly platform wells, they tend to slump with age. I don't think the reason for that is fully understood, but we've seen movement for a number of reasons. Either pipe failures is a reason for movement of platform wells, but we do get movement in the soils as well. We get compaction of reservoir sections and slump of the overburden as well, and all of these. So with any movement of the well, there's always a redistribution of loads. Those images there, you can see there's a conductor casing in a pretty poor condition there in the top right. It's holed right through. To the left of that is that's a schematic of a PEC reading. That's a pulsed eddy current tool that's been fed down a D-annulus and measured wall thickness there. You can see that bottom picture is a wellhead that's keeled over to the side. So deterioration makes wells complex, even if they're originally relatively simple wells. The deterioration of them has made the situation complex to analyze. So how do we address these situations, and how do we get the best data? Well, we use their software tools. The tools that we typically use for a well situation is we use them to perform casing and completion stress analysis. We use software tools for casing wear analysis, and we also use the global engineering tools for that kind of environmental analysis. And occasionally we use detailed FEA tools to do detailed engineering. These tools are all good. They're specialist in their own frames of reference. They're not generalist. Well, apart from the last one, the detailed FEA engineering tools. Detailed FEA is quite a sort of blank sheet. It can be used for many applications. But the other tools that we use are very kind of pigeonholed. So looking at the casing and completion stress analysis tools, Wellcat is the one we use, mostly because of its thermal engine. It's a very competent thermal engine, but it has its limitations. Firstly, everything's a pipe. That's a picture there of the pipe inventory, and nearly all of the items that you're expected or capable of modeling is a pipe of some description. Everything is axis symmetric. It does allow, Wellcat in particular does allow dual tubing, but apart from that, all of the strings are axis symmetric, so no lateral deviation. Loading of any pipes from the vessel or environment is ignored. It's purely a well simulator, so we're talking about changes in pressure and temperature. That's what makes the load case. There's no option there to put in any vessel loading. Any lateral movement is not allowed. It does axial. It shows axial expansion and contraction, but lateral loading is not accounted for. Any compensated strings not accounted for again. So the DST string that was on the previous slide, that's obviously on a floating rig. That's obviously compensated, but there's no option to put that in there. And this is a global type FEA tool, so it doesn't do detail very well. It's global tools. They look at the large elements or large nodes, but not in high detail. Casing wear analysis. It's quite mature. String positioning models. It does. You have options for soft and stiff string. They're pretty mature. They can calculate the contact force as well, and that's what casing wear is highly based on. The problem with these packages is to get accurate wear prediction, we rely on a wear factor, and that's a bit of a sort of figure that's pulled out of thin air. There are Moore's tests, and there is, the hard banding vendors will give data on wear factors, but it's quite difficult to replicate and have confidence in that wear factor. A lot of people view it as a bit of a fudge factor. In general, when we do the simulation with the software, the shape of the profile is good. It's assigning a magnitude to it that's difficult, and that's mostly because of the wear factor. So the nicest method, if you have the data, is to do calibration runs with analogous operations. So if you have any measured data from analogous wells, if you can calibrate that and calibrate a wear factor, then you can use it. And if you can get a good calibration, you can assume that your wear simulation is going to be reasonably accurate for the upcoming operations. Global marine engineering tools. We have a couple actually. We use Flexcom and OrcaFlex. One of the big emissions from these is the fact that the internal casing completion loads are not modeled. It's not really that kind of tool. That was never its task. These are accounted for, but they're added manually, and usually it's a geothermal Boyd weight assumption that's put into the model. The models set a boundary condition about 50 meters below mudline, so they're not really interested in what the rest of the well is doing. It has no ability to assess the string loads under the correct operational conditions. So all of the temperature effects, so particularly platform wells, we see this. Well, one of the case studies at the end investigates this. The string weights, their effective weight is highly affected with temperature. So cold strings will contract and pull down with way in excess of their Boyd condition. And likewise, the reverse hot strings will unload themselves on the wellhead, and that's why we get the resultant wellhead movement. But the change in the effective string loads can fluctuate substantially with changes in temperature and pressure. And with those changes in loading, this affects a lot. It affects the strength and stability of surface conductors. These are particularly platform wells, we see this, and it even affects the damage that they accrue with through fatigue. And then we get onto the detailed FEA analysis. It's a detailed FEA. The FEA tools we use, ANSYS is the one that we use mostly. It's not specific. It's pretty much a blank sheet. Its level of detail is capable of very high levels of detail. Its level of detail is excellent. But that, in effect, is the software's Achilles heel. The reason that the other packages have been made specific is for speed and ease of use. And the fact that the FEA tools are not specific and haven't been streamlined to a particular function makes them time is the commodity that they require, and that's not always particularly practical. So what's the answer? Well, the approach that we've adopted is a combined simulation solution. So that's our acronym there, CSIM. All of the specialist pieces of software can be combined, and by using them all in their own sort of areas of expertise, we can replicate the real-world conditions more competently. So the process we use is we use all of the required software packages and their capabilities. Once we have outputs from one, we transfer the relevant data to the other packages and create that workflow. And then we assess the impact and realize the contribution of each one. Obviously, some loading mechanisms might be more significant than others. And then if required, we move on to detail and kind of zoom in and look at detailed FEA engineering of the items that require it. But basically, we're trying to combine all of the specialist areas of the pieces of software, combine the loading mechanisms, and get the true picture, or a sort of closer to real life solution. The best way of viewing this, so this is a typical workflow that we would do. We've got WellCat and FlexCom there. So WellCat is our well simulator, tubular design package. FlexCom is the environmental marine package. We've got ANSYS up there at the top. It's quite mature. The relationship between FlexCom and ANSYS is quite sort of well entrenched in the industry. The idea is you do your global analysis in FlexCom, and then if required, you take those and apply them as boundary conditions to things like a detailed wellhead stress analysis in an ANSYS model. So you apply those boundary conditions from the global package and apply it to the detailed ANSYS package. There's no reason why that can't be done with WellCat as well. WellCat is a global tool, but analyzes wells. You can take those boundary conditions and apply them to a detailed ANSYS model of a tool or any kind of component in a well, and get a much more detailed analysis. The other one there is casing wear. That's another Halliburton package. We use casing wear to derate the tubulars, and then we model the tubulars. So that would be a typical combined engineering, combined simulation workflow. So now some case studies that give us some examples of how we've used this methodology. I put a little header in the top right-hand corner there to show which packages we used. This was a completion analysis, and particularly of interest to the client was the ESP pump. You can see an image of it there. This was a dual function completion, so it was quite unusual actually. It was simultaneous oil production and water injection, so pressurizing, pressure maintenance in the aquifer. To perform this, they had that on that schematic on the right there. You can see the red insert string. That was a small string of pipe, and they're injecting high pressure water down the inside and through the bypass leg of the pump. Simultaneously, the pump is pumping oil from the A annulus, and it's pumping it up the annulus between the insert string and the tubing. So it's a pretty complex situation. So this is an example of why this complex situation arrived, was because of a component in the well, and it was this pump in particular. How do we model this in WellCat? WellCat has no ability to model dual legs of a pump. So it's a very complicated situation. How we model it in WellCat is basically we ignore the pump leg, and we just put the bypass leg in there and ignore the pump assembly on the side. The question is, well, the WellCat analysis resulted in a breach of the bypass leg connection in compression. But how do you have confidence in that result? There isn't enough detail, and all you're modeling is the bypass leg in isolation. It's not modeling any cross bracing with the pump body, so how can you have confidence in that result? So what we did was we generated an ANSYS model of the pump, relatively simplistic. Obviously, we don't want to spend a sort of disproportionate amount of time putting together the model. So relatively simple model of the pump assembly, getting the correct stiffnesses. We simulated the cross bracing between the two. Obviously, that supports the bypass leg. ANSYS is a perfect world. We had to put in a small perturbation to instigate any buckling if it was to occur. And then we extracted the loads from WellCat above and below the pump and we applied them as the boundary conditions in the ANSYS model. And this is what we saw. We did in fact see that the pump leg was the bypass leg was buckling, and the bending moments that were induced in that bypass leg wear out with the ratings of the connections in the bypass leg. It was kind of a pressure differential buckle that was causing this buckling, but there was a failure or a breach. It was out of limits. They were planning the client was planning on running 12 of these completions. Now, the cost of ESP pumps and these type of completions is substantial, and the cost of 12 of them, if this had gone ahead and they'd had problems, they basically would have been pumping up their own injected water if this bypass leg would have leaked. So obviously that would have been quite a significant problem with the well. There was going to be 12 of them. So that was a good example of how we took the boundary conditions from WellCat and applied it to a detailed ANSYS model. The second one is, I know we've talked about platform conductors quite significantly. The second one is a good example of how the well loads themselves, the loading of the inner strings, the casings and the completion, affect the behavior of the conductor. In this project, we looked at a North Sea platform conductor. It was actually a HPHT well, and there'd been some problems with the installation of the centralizers. 4 centralizers there, and you can see that the engagement with the guides on the jacket. There's 3 subsea and one dry one there. You can see that the engagement was very, very small. It was like, some of them were less than an inch. These were HPHT wells. The client was concerned that under hot production, that there would be enough conductor movement to disengage the centralizers from the guides. So they asked us to have a look at this and do some analysis. So the first thing we did was to calculate what kind of load, thermal load, that conductor was going to see. So that's when we went to WellCat. You can see there, the top right, we used WellCat and FlexCom in this instance. You can see there that this is a substantial well. You can see that the conductor is in 470 tons of compression at the end of build. And then when the well is put onto production, you can see there's a massive change in conductor load. It's close to 600 tons. And these wells were so sufficient temperature to actually put the conductor into tension when the well was put onto production. That's how hot these wells were. So we took this data and we applied it to FlexCom model of the conductor to look at the marine analysis and the effect of the environmental loads on it simultaneously. We did 2 simulations. We did one with the assuming that the well was cold and the conductor, the centralizers were all engaged with the guides, and then we did a simulation with the well in its hot condition, and only the top guide 1 was still engaged. The other 3 guides the other 3 centralizers had disengaged from the guides. And you can see there the stress utilizations. The one on the left, that's the cold one. You can see that it's obviously in a good condition with the guides engaged. And then what came as a bit of a surprise was the fact that with the lower 3 guides disengaged, we're still in a pretty good condition there. You can see the stress utilizations are still relatively low. And that was a case of, although there was no lateral support for this conductor, the sheer the internal casing loads and their tensioning effect on the conductor had stabilized it. So it's quite an unusual situation. It shows what kind of impact the internal well loads have on any kind of conductor analysis. Now, it doesn't mean to say that any kind of remedial action wasn't required, but it certainly implies that the urgency for any kind of corrective measures is certainly reduced. Lastly, we look at subsea wellhead movement. This project actually involved all of the packages that we've put in that workflow. So we did some well work with WellCat, we did some environmental work with FlexCom, and we did some detailed analysis work with ANSYS. Subsea wellhead movements, subsea wells not really considered to move that much, but they can do. This one had a lock ring failure between the high and low pressure housings. The WellCat was used to check for the safe operation of the well and to check that it was safe to continue operation in that condition. Some of the effects that had caused this lock ring breach, there was a number of, in the oil industry we like to call this the Swiss cheese effect. There was no one mechanism which caused the lock ring to fail. It was a number of things which had combined to cause this loading of the wellhead structure. Tree landing springs basically meant that the high pressure housing wasn't supporting a full tree weight. In the well construction, you could see that reading the drilling reports, some of the casings had been worked down, so maybe they didn't achieve their full hanging weight. The type of completion, it was an HSP pump, and so insulated. There's a lot of power fluid, quite high pressure annulus fluid. It's also insulated as well, so the circulation of the power fluid to the pump gradually gets warmer and warmer. So although the wells went that warm, they had a sort of disproportionate heating effect due to the insulated lines and the circulation of the power fluid to the pump. This wasn't a standalone well. This was on a template, so there was obviously thermal interference between multiple wells. There were some other factors as well. They took some losses during cementing, so there was quite long free lengths that were available to thermally expand. And even the casing configuration itself ended up with wellhead pressures exposed to quite large piston areas on the underside of the wellhead. So the first thing we did was we checked the well was safe to operate in that condition. So this was our WellCat analysis on the well. We adjusted it to replicate the upthrust and the upwards movements and the change in load distribution between the strings. And you can see there we're quite sort of comfortably within limits on the two design limit plots on two of the strings. So there was no issue with continuing operation of the well. When we did the load analysis, it's quite surprising actually. I mean, the temperature profile of these wells, you would never have thought that the wellhead would be in a sort of upthrust condition. But we calculated that only 67 kips of downwards force was in the strings. The submerged tree weight was reduced from 69 kips to 36 due to those tree landing springs. There was a large piston force, 185 kips of piston force. We did the analysis, and with these figures we simulated a failure of the lock ring to see how much the well could possibly move, and we calculated a 25 millimeter upwards movement. The actual measured an ROV kind of estimate on how much the well had moved gave a 30 millimeter movement. And when we applied any kind of bending load to that, from the FlexCom analysis that was obviously used for the riser analysis, it showed that the additional bending loads, it was likely that the rating of the lock ring was going to be exceeded. So again, three studies there, three case studies there, which show that the difficulties in assessing complex well solutions and the value of transferring data from one package to the other. This project, in fact, finalized with an FEA analysis and repair mechanism in the form of a clamp. FlexCom was also used for this as well, because obviously the clamp has to take some marine loads. So in summary, the real world is a complex place, and using pieces of software in isolation, which is commonly done, doesn't really capture those complexities in the real world conditions. Using them in combination and transferring the data from one to the other can give you some quite substantially different results and more accurate results. So I guess the rules are make your analysis as realistic as possible. Include all of the load mechanisms. If it's a platform conductor, you've got to include environmental and well loads simultaneously. There's some situations which really make a huge difference. The combined engineering, the method we use, you don't know which way it's going to go. It could make the results better or worse, but either way you need to know. You just need to know. You just need to work on the best data, and it's only going to help. It's going to help you make the best decisions. So firstly, obviously safety, practicality, or the most effective solution, and you're not going to be spending more money than you need to. So that's the summary, basically, and now I'd like to open to any questions.
Okay, thank you, Dave. That was great. We've already had quite a few questions, so I'll go ahead and ask you those. So the first question, apart from the conductor that you talked about in the case study, have you seen other situations where casing loads have affected the conductor performance? And do they generally help or make things worse?
Yeah, that's a great question, actually. It would be hard to say for a specific situation if the casing loads helped or hindered for a particular scenario. We've seen some unusual trends. For example, conductors can stabilize themselves under high compressive loads. And then they can be in worse conditions under medium compression. That's not particularly intuitive. We think that once a certain value of compression is reached, once that magnitude is reached, the deflection of the conductor can almost wedge the centralizers harder into the guides and get them to make contact. And that kind of stabilizes it. So if I was to sort of give any advice on this, I'd say to include well loads in any conductor analysis was a good idea. Either whether you're in the design phase or the integrity, if you're analyzing an existing platform conductor, it's best to catch them early and do some small remedial fixes than have the headache of a failure and trying to address that, and it's going to be costly as well. I hope that answers your question.
Thank you. The next one is, are subsea wells commonly checked for lock ring failures?
No, I don't think so. They probably should be. We've had a number of requests about subsea wellhead movements. When it's noticed, it's usually some kind of abnormal movement in the wellhead. This is the first one I've worked on with a lock ring failure. Lockdown in general is we've done a number of projects. Typically, we look at lockdown of casing hangers under blowout scenarios. That's quite a common kind of lockdown analysis, and I guess that's similar logic. But yeah, I would certainly recommend subsea wells are checked for their loading, wellhead loading. Yeah, definitely.
Okay, next question is, how easy is it to model degradation like corrosion and well slumping, and can this approach be used to investigate the causes of slumping in platform wells?
Yeah, it's quite tricky to model. It does rely on data and initial well build data. So platform wells that have slumped are generally quite old, and with that, as a sort of function of age, comes obviously problems with the data of the well build process. And we've used a number of different sort of bits of data to try and assess the original position of wells. It's quite a difficult thing to do. If you can calculate how much the well has slumped, you can pretty easily do the redistribution of the loads among the strings. But yeah, it's not easy to do that. And accounting for the corrosion as well, it relies on a measurement. So PEC tools are quite good. Those pulsed eddy current tools, they give a good idea of the amount of material loss, and you can certainly put that in. And once you decrease the cross-sectional area proportionally and apply the load, you can see whether your string is going plastic over the corroded area.
Okay, next question. Why do you use WellCat as the tubular package?
Yeah, there's a number of tubular packages out there. I think I think it's mostly because WellCat has kind of become the industry standard, really. Most of our clients have it, and they use it as well, and they know it, and it's been used long enough so it's trusted now. Its thermal engine is excellent. I've been using it pretty much every day for 15 odd years, and it's always pretty much matched measured data consistently. If I've ever found it to be out, especially on the temperature side of things, if I've ever found it to be out with measured data, it's normally I've made a typo or something in the model. You recheck it, it's pretty much bang on 100% of the time.
Okay, next question. We're trying to use our design models to justify additional operations on some of our wells. In your experience, how closely do as-drilled wells tend to match the intended design?
They do tend to be the ones we've looked at when we've done as-drilled modeling. That's a good question. I would highly recommend that people do as-drilled modeling. As soon as the drill bit hits the dirt, it's a busy time for a drilling department. So they don't tend to re-look and update the model with actual data. Putting in the correct values, the correct tops of cement, and the correct shoe depths, and all of the timing of the construction operations. The ones we've looked at where we have done as-built modeling, the wells have actually been significantly better. The design process is quite pessimistic as to what condition the well is in. So the ones we have looked at have been significantly better. But it is a marked change. What you planned to create is substantially different from a mechanical point of view to the one you actually put in the ground. So I'd highly recommend that you do real-time modeling of wells.
Okay, and I think this is our last question. How can your analysis approach help us deal with the big gaps we have in the available design data for our wells when we're planning intervention operations?
Intervention operations. Yeah, I mean, it can be. WellCat is a big one because you need a package with a thermal engine. So you can't make thermal assumptions. The packages that you use that don't have a thermal engine, you make a thermal assumption. So you're not really replicating real life. What you want to do is calculate the real temperatures that you're doing. So any intervention, you model the actual temperature changes and the pressure changes that are going to be caused by that intervention, and then any kind of combined loading situation, as that sort of that Venn diagram we looked at, combined loading situation as well. Capture everything from the environment to the well conditions and what you're actually going to affect the well by that intervention. But yeah, capture everything is probably the best way of ensuring that an intervention isn't going to do more damage than good.
Okay, great. Well, thank you so much, Dave, for all the information on the topic. That's all the time we have for today, but as we mentioned earlier, if we didn't get to your question or if you'd like to continue the discussion, you can contact Dave directly using the details provided here. And thank you to our audience for your time and participation. We hope you all found this useful and will join us for more webinars in this series happening every 2 weeks during our time at home. And you can check out the 2H website for more details and to sign up. And again, please look out for a recording of the webinar in your email in the next 24 hours, and we hope you all enjoy the rest of your day. And thank you.